Swayam Prabha. Digital India. Educated India.
Before we do that, I'll just give you a couple of very quick examples so you understand the distinction between discrete and continuous. Number of visitors or customers, number of defects, number of defective parts, number of complaints received. So anything that's typically like a number, right? Very conveniently, it's discrete. Anything that you're counting makes sense that it takes on discrete. Anything that can only take on discrete values also, okay? Examples of continuous are things like amount of time it takes, some measurement like length, width, area, volume, temperature, profit in rupees, return on investment as a percentage, proportion of a certain chemical in a thing. Now, the major distinction that I want you to make in understanding the difference is some things are inherently discrete or continuous based on their property, not based on your measuring device. Right? You can always make an argument that, look, why are we doing all this? My stopwatch only measures up to seconds. So if it's 5 seconds, I'm not getting any other reading. I can, so you drop the ball and I start the watch. The answer can be 5 or 6 or 7 or 8 or 9 or 10. Can't I just think of it as a discrete distribution with these discrete states? And the answer is you can. There is nothing that stops you from doing that. But the discretization itself is problematic because you're losing resolution and you don't need to do that. Right? You have a conception that does not require you to do that. But if you did that, you would not be doing something mathematically inaccurate. But what you would be doing is you might not be able to capture how the density changes from 5.5 to 6. So suppose actually, so you'll have a you'll have a response, right? The probability it can be 5 seconds is some number. Probability it'll be 6 is some number. Now what if actually between 5 to 5.5 is very different from 5.5 to 6? That loss of resolution is something that you have forced upon yourself through the discretization. Sometimes it's a convenience, but you don't have to do it. So it's never a preferred thing to actually do. Now, the flip, however, so we've just spoken about the discretization of a continuous random variable. So that's something that there's no necessity to do it, and because you can represent it in the continuous space, and you can answer all your business questions or research questions with this conception, right? And we're going to talk about how to do that in a few seconds. But there is the flip also. There are some times when truly what you have is a discrete random variable. So let's change this question from one of answering questions right, correct, to a random variable like how many people would apply for the ACM summer school in data science. Okay? You can argue that before we open the registration portal and so on, it's a random variable. You agree with me on that, right? Now, I can argue, and I would argue correctly, that it's a discrete random variable because there are some countably finite number of registrations that can happen. You would know that the number can technically not be less than 0. So you can have 0. It can be 0 with some probability because the link is broken or something stupid like that. Then you can have 1, 2, but you can't have 2.5 registrations. So I'm fine reasoning that this is technically a discrete random variable. But take a look at this random variable. It takes on really large values, right? So it's taking on values between 500, 600. We had close to 1,000. Now, each of these probabilities need to add up to a 1. So each of these probabilities are really small. So many times, it's convenient to actually take a variable that is genuinely discrete, but one that has so many states. It's kind of like the time which could have so many states. In fact, it technically had infinite states, but it's very convenient to take situations like this and think of it or model it as a continuous random variable. So you almost never want to do it one way. The other way is, in fact, convenient or preferred. Okay, so now let's get into a little bit of the math. Okay, so we spoke about this thing called probability mass function. That's used for a discrete random variable, x, with possible values x1, x2, x3. Now this is going to be a recurring nomenclature, which is you represent a random variable with a capital letter. Okay. Now you use small letters to represent the outcomes that the random variable can take up. Often in many texts that's just referred to as the variates. So you have the variable which captures the phenomena, and then individual outcomes. So I can talk about the time it takes to drop the ball, and I call that the random variable. But if I drop the ball a given time and some guy clocks it, that's one precise number. That number, which is the manifestation of that random variable, is the variate, and that's all often referred to in lowercase. Okay, so you have this, the random variable in uppercase, the variates in lowercase, and a probability mass function, like we agreed, is nothing but where you have this function, and for this function, if I sit and substitute each value x1, x2, x3, and so on, it precisely returns to me the probability that this random variable capital X can take on this value xi. Does this make sense? Okay. Therefore, it must follow that for any particular xi that I substitute, the value should be between 0 and 1. It should also follow that if I add up every possible xi, that is, I go from I is equal to 1 to n, if there are n outcomes, I should be able to get 1. Okay, when I sum this. So just so you internalize that f of x is in fact a mathematical function. So this is an example of f of x. Okay, so what will happen is, if I can have, these are the possible outcomes, so I should declare that this is applicable only for these outcomes. I can't substitute 6 and say that's a probability of 6. So in fact, more often than not, it's defined in this way. You'll have a function f of x, and you will say this is for x is equal to 0, 1, 2, 3, and then you'll say it's 0 otherwise. So you just dot, dot, dot. Okay? Okay. And you can actually play around with this. You can substitute the different values, and you will see that you'll get individual probabilities. You'll also see that when you add each of them up, you'll actually be getting 1. So this is an example of a probability mass function. Okay. Now, we're going to define something new called the cumulative distribution function, and this thing called the cumulative distribution function captures the probability that this random variable takes on a value less than x, less than or equal to x, to be precise. Okay, so when small f of x was some mathematical function where you can substitute x, and what did it tell you? The probability of x occurring. Capital F of x, which is the cumulative distribution function, tells you for any given value x, what is the probability that I will get a result less than or equal to this value. Okay? And understandably, how do you figure out what this is? Well, I know it's really simple. With probability mass function, the probability of getting a value is just small f of x. So if I wanted to know what is the probability of getting values less than or equal to some value x, I just take all the values that were less than it and substitute it in the small f of x. Right? So what I'm going to do is, I'm going to take every xi that is less than or equal to x, substitute that in f of xi, and start adding them. Right? I am interested in capital F of x. What does capital F of x mean? It means the probability of getting values less than or equal to this value called x. So remember, this is small x, which actually means some number. I'm walking in here and saying, what's the probability you get a value less than 3, less than or equal to 3. So what should I do? I should count probability of getting a 0. There is small f of x of getting a 0, small f of x of getting 1, and I'll do this for every value till 3. And when I add them all up, that's what my capital F of x actually is. Okay? Again, capital F of x should be between 0 to 1. Understandably, right? If there is a value x which is less than or equal to y, capital F of x should be less than or equal to capital F of y. Are you capturing the intuition behind this? See, x is less than y. The probability of getting a value less than x is what capital F of x is. Y is greater than x. So probability of getting a value less than y will include the probability of getting a value less than or equal to x plus maybe something. Therefore, capital F of x has to be less than capital F of y. Now, if I substitute the highest possible value in small x, what should capital F of x be? 1. If I substitute values higher than the smallest possible value, it should still be 1, right? Even though it does not include the sample space, I'm still on the number line. So everything to the left of me in the number line should still be 1. Same way, if I substitute the smallest possible value less than the smallest possible value, because it includes that value also, my capital F of x would be 0, because the possibility of getting that value or less is actually 0. Okay. 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 So now we've discussed the PMF and the CDF. Now let us move to a couple of interesting things that we'd want to capture in the PMF or CDF, besides the PMF or CDF, which is mean, which is a measure of central tendency. So there are multiple measures of central tendency. But if you just came and told me this is the random variable, this is the function, this is the sample space, these are all possible values you can get, I might be interested in a little bit more. I might be interested in what is a typical value, right? What should I expect in general? What is a central value, right? And to do that, what we're going to do is we're going to define this thing called expected value, which is nothing but you sum over the entire sample space. Okay, so you're going to, what we mean by summation over x means you go to each and every element which can be an outcome in the sample space, take x and take f of x, okay, and multiply them and add each one of them up. So why are we doing this? Suppose I told you that you could have one of 4 outcomes. Okay, the outcome can be either 1, 2, 3, or 4, and they're all equally likely. Now, what would be your expected value there? So here we're not necessarily talking about, now each of them is equally likely, but we're not talking about which one is most popular. So it's a slightly different definition. We're not talking about which point has equal number of outcomes on either side. That would be another definition. So the first definition, which I said, which is most frequently occurring, would be something called the mode. This other definition I can take of central tendency. Like I said, there are many definitions of central tendency. The other one could be to see which outcome has equal number of outcomes on either side. That would be the median. But sometimes I'm interested in a slightly different definition. And this definition says, the easiest, so I can define it in one or two ways, but you can think of it as a weighted average, right? If it's all equally likely, you would just have 2.5, right? You had 1, 2, 3, 4, so 2.5 if it's but what if these are not equally likely? Then you'll have to account for the fact that some are more and some are less. There are different definitions you can give. One definition would be to say, if you were to pick a value such that the distance between that value and each outcome, when squared and added, is minimized, that would be the mean. So this is a slightly more convoluted definition but it's a very useful definition across the board. So let's say you had all these outcomes. 3, 4.5. I'm just putting some outcomes, 2.7. So this is some data set that I have, right? And I'm asking myself the question, if I can pick one value C such that the distance between C and each value that I see in the data set. So you can think of each value in a data set, or you can think of each value weighted by how likely it can occur. Both are fine. So I can imagine I gave you a data set. That's one way of thinking about it. The other way is I take each outcome, but I weight it by how likely it can occur, right? If I ask myself a question, now I can take C and I can measure the distance between C and 4.5. Okay? I can take C and I can measure its distance to 2. Right? Now, if I ask you the question, can you pick a C such that these distances squared and summed should be minimized. It turns out that the C is the mean. And we can come up with 2 or 3 different definitions itself of the mean. People like to think of it as the first moment. So it's kind of like if you had all these numbers in the number line weighted, where would you put a fulcrum so that the whole thing is balanced, right? You never always put the fulcrum necessarily in the place where there are equal elements on either side, right? So in a seesaw, if one side is fatter than the other side, the fulcrum is not in this exact center, right? It doesn't matter the number of agents, it matters the weight, how far they are away from the seesaw. So this is fundamentally a different measure of central tendency. One way of thinking of it from an estimation perspective is to think of it as that value that minimizes the sum of the squares from a given point. The other way of thinking of it is the first moment, where is the fulcrum on the number line. But understandably, what you should do is there's the arithmetic mean, which is nothing but the sum of all numbers divided by n. But that's different because here you just have individual outcomes. But each outcome needs to be weighted by its likelihood. So what we're doing is we're taking each outcome, which is x, and then we're weighting it by saying how likely is x to occur. Okay. So that's the measure of central tendency. The next one that we would be interested in is the dispersion. So what is the dispersion that you see? And when it comes to dispersion, you basically, we define this thing called variance, right? And variance is nothing but each value, each possible outcome that can occur, minus the mean. This mu is what we figured out here. So we're saying you can have the same central tendency, but the dispersion could be different for different values. So how much does each data point, how much does each outcome deviate from the expected value squared, and you want to square this because some deviate on the positive side and some deviate from the negative side. Now if I squared everything, you just had some measure of how much things are deviating, but most importantly, I also need to weight this by f of x. Now remember, this distinction between arithmetic mean, arithmetic standard deviation versus expected value and variance. If I just gave you 20 data points, I would do the same thing. I'd take each data point, compare it to the mean, square it, right, and move on. But here, I don't have data points. I'm just given outcomes in a sample space. And so for each outcome, I do this, but I need to weight it by how likely is this outcome to occur. Now, you will often see a form that is, this to me is the most intuitive form, but you'll often see a form that is written a little differently. And it's fairly elementary algebra to move from this equation to the equation below. I won't actually do it here just in the interest of time. But if perhaps this could be a tutorial question where you could just, it's simple, a minus b squared, you do the expansion of a minus b squared over the summation, you will get the form below. And it turns out that the form that's there below is just more convenient for various mathematical operations. Okay, and you all probably already know the standard deviation is nothing but this square root of variance. Okay, so we spoke about probability mass functions, right? Now we're going to talk about probability density functions. With probability density functions, you no longer can talk about the probability of a particular outcome. So in other words, I can't give you one particular value and say what's the probability of that, for multiple reasons. One, that's not what the PDF is supposed to be. We never said the PDF is the probability of the absolute likelihood. In fact, the PDF is often referred to as the as characterizing the relative likelihood, not the absolute likelihood. The absolute likelihood would mean if I give you an f of x, you plug in an x, you get the probability that x can occur. That's not what the PDF claims to be. PDF says, I'm only giving you the relative likelihood. So what does it mean? What it's supposed to try and capture is within a range, I can tell you what the likelihood is. Okay? So therefore, what is the probability? So suppose I actually, so I've told you, if I give you an f of x called the PDF, and you substitute x, you're going to get a number. And I've told you that number is not the probability, right? So what is the probability of that particular outcome? So I've told you, if I give you a PDF called small f of x, that's a formula I've given you. Okay, deal? And then I'm interested in knowing what's the probability that it takes 5.7 seconds exactly to drop the ball. I've told you, you can't plug in 5.7 into this f of x. You will get a number, but that number is not the probability. But in that case, what is the probability of the ball taking 5.7 seconds to fall to the ground? How do I get that? Keep this question in mind. We're going to address that in a few seconds. Okay, so now I've told you that substituting 5.7 is not the way you should use it. So how can you use it? Well, you can use it by saying, you can define the way you're supposed to use it is by saying, by giving it an A and a B. You can say between 5 to 7 seconds, what's the probability that the ball will drop to the ground? Then you can use what I'm giving as the PDF. But how do I use it? The way I use it is by saying the area under the curve. So the PDF, the f of x itself can give me some funny looking curve, right? And if I give you 2 points, A and B, the way I can use, so this is f of x. Okay, so this is f of x. The way I can use f of x, I cannot use f of x by substituting a value x and getting a number and claiming that's the probability. That would be the absolute likelihood. How can I use small f of x? I can use it by saying the area that I get under the curve from A to B is the probability that x will lie between A and B. So when I give you a PDF, the way you could use it is by saying this f of x, I'm going to substitute values A and B, 5 seconds to 6 seconds. I'm going to drop a ball. What's the probability that it'll take between 5 to 6 seconds? I can do that by taking this value A and B and looking at the area under the curve. Mathematically, how would you look at areas under the curve? You would integrate. So you would take f of x, you would integrate it from A to B, f of x dot dx, and that will give you a number, and that number is the probability that it will take between 5 to 6 seconds for the ball to drop. Now let's go back to the question of taking 5.7 seconds and substituting that. And when you substitute that in f of x, you'll get a number. But I've said that number has nothing to do with the probability it will take 5.7 seconds. Now that you have this conception, how will you figure out the probability it will take exactly 5.7 seconds when you drop a ball? So you have 5 and 6. That's the range. So here I gave you a range. I told you what is the probability the ball will take anywhere between 5 to 6 seconds. And I gave you an f of x. And I've told you a method. I've told you you can integrate from 5 to 6, put in that f of x. You'll do the integration, substitute the b and a, and you'll get a number, and that number is correct. Now I'm saying, now I've told you how to answer this question if I ask you the question between 5 to 6 seconds. Now I'm telling you, for it to take 5.7 seconds precisely, you drop the ball, it takes 5.7 seconds precisely. What's the probability of that? Why? Okay, explain it to me in terms of what I've just taught you. Right. So the answer that everyone is in, for the benefit of the camera, there's answering that it should be 0. And the answer they're giving is it's a discrete point, all of which is fair, right? But basically, when I gave you 5 to 6 seconds, you could integrate from 5 to 6. So here, what would the integral look like? It'll be from 5.7 to 5.7 essentially, right? In other words, the area under this curve, as A and B become exactly one precise point, the area under the curve becomes 0. That is helping you understand from a mathematical perspective. But this should also match our intuition. Why is it that intuitively, if I told you what is the probability it will take 5.7 seconds for the ball to drop, why is it that you turn around and say it's 0? Okay, you define PDF this way, I agree with you. If this is how you're defining PDFs, it makes sense. But why is it intuitively 0?
It's continuous and it's real, so it could be 5.77.
Right, so it can take on any number of possible values. So asking a question like what is the probability of it being 5.7 is as unique and bizarre as asking the question what is the probability it will be 5.70321497639, and I can keep on going. Those are both numbers that occupy the same amount of space in the number line because there are infinite such values. So if each of these values took on some positive density, it wouldn't, you'll have infinite such values. So the occurrence, and this is an intuition that's kind of hard to come by, so it's worth spending a few seconds on this, that the probability of any given point is 0. That is matched with the math we saw in the form of the integration and the areas under the curve, but it also should match our intuition that the only reason 5.7 is possible is because we might have a range in our head that anything between 5.65 and 5.75 belongs to that category. But 5.7000000 going up to infinity is as much, as bizarre as another number that is not ending in the number line. Okay. So now that we've defined continuous distributions, we can safely say f of x should be greater than or equal to 0. You can't have negative density. If you integrate from minus infinity to plus infinity, right, f of x should be equal to 1. Now, it's many texts will, some texts will always say minus infinity to plus infinity. That makes sense if the distribution goes to minus infinity to plus infinity. Minus infinity to plus infinity is just a safe placeholder, right? You can just say minus infinity to plus infinity, even though the density technically does not go to either x. What you really mean is from the lowest possible value to the highest possible value. And the probability at a given point, as we've already discussed, is 0. Okay, so now we move on to the same thing, the cumulative distribution function. And the cumulative distribution function is again the same definition, probability that this random variable x takes on a value less than or equal to a small value, a particular value small x, right? And what did we do with the discrete version? We were actually able to count. We took each outcome that was less than x, took its small f of x, and added it up. Unfortunately, here we can't because how many such values of x are possible? Infinite such possible values. So what do? We again integrate. We integrate from minus infinity to x, to that point, right? The same function, the PDF, and you can use u or y or anything else. That's just a placeholder because when you integrate it, ultimately you're going to be substituting x. So instead of summing each outcome, you basically look to see what is the area to the left of the curve. So if you had this small f of x, and let's say this is small f of x, I'm going to call it small f of u, just some other variable. Now capital F of x would be nothing but you go to that point x, right, and say what is the density to the left of that curve. And the density to the left of the curve is nothing but minus infinity or whatever is the lowest possible point to x of the PDF.